Good afternoon, everyone. Welcome to the ninth week of the discussion session of the course Strength of Materials course offered by NPTEL. The course instructor of this course is Professor Sriman Kumar Bhattacharya, is a professor from IIT Kharagpur. Myself, Asif Raza, I am a TA. I am a PhD scholar from Department of Civil Engineering, IISc Bangalore. So today we'll be discussing questions relevant to assignment number 9. Uh, and yeah, so let's start without waiting. Okay, so uh, before directly asking questions, first thing I'll just uh, ask you all to give you some suggestions that it's best to remember some of the deflection and moment or the slope formula, so that it might help you to directly calculate as early as possible. That will help your time. So first thing is, take the case of cantilever beam. Cantilever beam. So first thing, uh, when there is a concentrated load P with the span length L, okay, and EI is um, the flexural rigidity. So the slope, or the deflection in this case that you need to remember, the deflection at the free end, it's equal to PL cube by 3EI, and the slope at the free end, it's equal to PL square upon 2EI. So it's best to remember this, because this would be used quite uh, frequently. So it's best to remember this. Okay, first thing, when you take the case of concentrated load. Second is when you take the case of UDL. Okay, and suppose the UDL value is W, the same thing, L and EI as the flexural rigidity. So in this case, the deflection is equal to W L4 upon 8EI, and the slope is equal to WL cube by 6EI. Okay, next one is when a concentrated uh, moment is applied at the end. Same EI. The deflection, it's equal to ml square upon 2EI, and the slope value is ml upon EI. Okay, so these are simple things which you can keep in your mind. Okay, so I'll just bring the A, B, A, A, B, and these are all values at B at the free end. Now, one more you can remember is for the case of simply supported beam. So, uh, the simply supported beam is the hinge at one end and the roller at the other end. The concentrated load, when it is applied at the midpoint, okay, L by 2 and L by 2. This is A, B, C. and EI is the flexible rigidity here also. Uh, in this case, it's best to remember delta C, and that is PL cube upon 48 EI. Okay, and one last one. Uh, okay, one last one that you can remember uh, is the case when there is a UDL. Okay, W is the UDL. So A, B, C is the midpoint, and vector EI is the flexural rigidity. So in this case, delta C is equal to the deflection at the midpoint is equal to 5 WL4 by 384 EI. Okay, so if you see in all of these cases, deflection and slope are inversely proportional to moment of inertia, the flexural rigidity EI, and it's directly proportional to the span length. So as we increase the span length, uh, the slope or the deflection value will uh, consequently increase, while if we increase the flexural rigidity, the values will decrease, be it the case of deflection or the case of slope. Okay, so this, like these five things I would ask you to keep in your mind. This will help you to solve most of the cases as quickly as possible. These are like the standard problems. Okay, now let's go into solving the questions now. That will help you to solve assignment number 9. Okay, so this first question is a quick review of the assignment number 8 question. So there is a question for a beam of rectangular section of width B and depth D, the maximum shear stress in the cross section for a shear force V is, and the options are 1.5 V upon BD, option B is V upon BD, option C is 2V upon BD, and option D is V times BD. So out of this, we can directly eliminate the fourth option, because if you see shear stress would be having a unit as in megapascal or Newton per millimeter square or meter square. That is kind of a force per unit area, and if you see the option 4, it's like force times area. So we can directly eliminate the option number 4. Now let's see out of first, second and third which of the options would be correct. So if you remember, this is a rectangular cross section, right? This is a rectangular cross section with B as the width and depth as the D as the depth, and the shear force diagram for this case is kind of this. It's a parabolic. So the maximum value, the tau max, occurs at d by 2. D by 2. Uh, okay. Now, uh, there are two ways we can pursue. First way is, as we know, it's a direct way, that tau max for the case of rectangular section it's actually 3 by 2 times of tau average. Okay, and 3 by 2 of tau average. Tau average would be force, that is shear force is V upon area, and area would be Vd, and that would be equal to 1.5 V upon Vd, and that would give me like option A as the correct answer. Now the second way which we can do is like is to calculate the shear force at the this mid section or the mid point. And if you remember the way to calculate the shear force, it's what V, right, VQ upon IB, and Q it's equal to area of the above section. So area would be B times D by 2, and the centroid of this area would be kind of D by 4 upon I would be BD cube by 12 and B. And let's simplify this. So we'll get 4 3 4 to the 8. Okay, V BD square upon 8. Here we have B square D cube upon 12, and this can be simplified as 4 to the 8 3. So 3 by 2 V upon BD. So that is what we got earlier. At okay, now moving on to the next question. Okay, if the depth of a simply supported beam carrying an if the depth of a simply supported beam carrying an isolated transverse load at its center is tripled, the deflection of the beam at the center will be changed by a factor of. Okay, so as I told you earlier, uh, the deflection, this is about the deflection, right? And this is the case where it's a simply supported beam, and the load is applied, transverse load is applied at the center. uh, so for this case okay, A, B and C, for this case delta C is equal to PL cube by 48 EI. Yeah, and uh, I is equal to, for this case, suppose I take the standard case, be it a rectangular section, so BD cube by 12, and this would again change, can be simplified as PL cube 48, this would be 4 BD cube. Okay, now we change the depth, so this is earlier. Now if I for the sake, like if the depth of the beam is tripled, PL cube by 4B, its depth is tripled, that is 3D cube, so it will be kind of PL cube 27 4 BDQ. So kind of delta C upon 27. So we can see it's like when the depth of the beam is triple, the deflection of the beam it reduces and it is changed by a factor of 1 by 27. So correct answer would be option D, 1 by 27. You can see it rather than solving a complete thing, you can also think it in a way that deflection is inversely proportional to area, moment of inertia, and moment of inertia is directly proportional to dq. So deflection would be directly proportional to, inversely proportional to dq. Thus, when d is increased by 3 times, uh, this will decrease by uh, factor of 1 by 27. Okay. Okay. Moving on to the next question. The question is, a simply supported beam with transverse loading was found to deflect more than a specified value. Which of the following measures will decrease the deflection? Okay. Uh, so the kind of loading is just says transverse loading. So what can we say that the question is the case. This is the case of simply supported beam, and there is a transverse loading. The transverse loading, be it like I apply uh, the transverse load, isolated load, or UTL as well. Uh, Now it says simply the transfer was found to deflect more than a specified value. Which of the following measures will decrease the deflection? So if we are getting a certain deflection for this case, if we want to decrease the deflection, what should we do? So if you recall, for a concentrated load, it was PLQ by 48 EI at the center, and the slope, no need of the slope. And for the case of UDL, it was 5 WL4 by 384 EI. So for all of these cases, deflection is directly proportional to L with some power. I would say I would just take N, and deflection is inversely proportional to E and inversely proportional to I. Okay, so these are the conjectures we can make using this thing. Now the question asks which of the following measures will decrease the deflection. So if you want to decrease the deflection, what should we do? Options are increase the moment of inertia, increase the span of the beam. Option C is select a different material having lesser modulus of elasticity. And option D is reduce the moment of inertia. So if you see option A and option D, it's quite contradictory. So we can think of like out of these two options, one would be for sure. There's a probability that it would be the one of the answer. Now let's see one by one. So first one, if we increase the moment of inertia, so this is the case, right? So if we increase the moment of inertia, since it's inversely proportional, our deflection would decrease, right? Now take the case of elasticity. So if we increase the elasticity, our deflection would decrease. Now if we increase the span of the beam, then deflection would increase, right? So if we increase, let's see, if we increase the moment of inertia, my deflection will increase. So yeah, this is what is required. If we increase the span of the beam, uh, uh, so deflection, would it decrease or increase? So it will increase, so this is not required. Now select a different material having lesser modulus of elasticity. That implies that E is decreasing. So if E is decreasing, my deflection would increase. So that is not required according to the question. So this is also not there, and this is also quite opposite. So our correct answer would be option A. I hope you can work this through. There is no issue solving this question. It's quite a straightforward thing. Just see it through. Okay. Now moving on to the next question. Okay, the question is, for a beam of rectangular section of width B, depth D, maximum bending stress in the cross section for a moment is. Okay, so if you recollect our flexural formula, it was M by I sigma by Y and E by R. Okay, so this is regarding maximum bending stress in the cross section. So we'll consider this first two relation, and let's take it M by I sigma by Y, and sigma can be written as M by I Y. Now to get the maximum bending stress, we need to have Y max, right? This for the rectangular cross section, if we are having width as B, depth as D, I would be equal to BD cube by 12 and Y max would be equal to D by 2, right? Then we can substitute it here. M BD cube by 12 and Y max is D by 2. If we solve it, it will come around 6m by BD square. So this is what we need, and consequently correct answer would be option A, 6m upon BD square. So this is I hope this is easy for you all. Now let's move on to the next question. So this is a very good question. The question is, the deflection curve of a simply supported beam AB. See the figure. It's of span L is given by the following equation. So we are given with the deflection curve equation. Okay. And the question is, the maximum bending moment on the beam AB is given by, and the options are minus q naught L square upon 2 pi square. Option B is q naught L square by pi square. Option C 2q naught L square by pi square. Option D 2q naught L square by 3 pi square. Okay, so to solve this question, if you guys must have seen in the lectures, so we are given with the deflection curve, right? Deflection equation, that is q naught L4 pi 4 ei sine pi x by L. Okay, now if you know this relation, that moment is equal to ei. So this delta I can write it as y. Okay, So its relation is given as d2y by dx square. Yeah, and d2y by dx square is actually the second derivative of this deflection curve with respect to x. So this is what we need to use. Okay, so first thing first, take the first derivative of e, and that is equal to minus q naught L4 pi 4 ei. If I take the derivative, it would be cos, just take this out, pi by L, and cos pi x by L. Okay, take the second derivative, it would be minus okay, minus q naught L4 by pi 4 ei pi by L whole square minus sin pi x by L. Okay, it can be simplified as d2y by dx square is equal to minus minus cancel out, pi square L square, so I can write q naught L square upon pi square ei sin pi x by L. Okay, yeah, so from okay, so this again can be simplified as d2y by dx square is equal to q naught L square by pi square sin pi x by L. Yeah, I can write it as 3. So from 2 and 3, m is equal to q naught L square pi square sin pi x by L. Yeah, now the question is asking about what is the maximum bending moment on the beam AB, right? So to find anything maxima, we need to take the first derivative of it and equate it to 0 to find the point at which it will be maxima minima, and we'll substitute that value to get the actual value. Okay, so for maximum bending moment, dm by dx equal to 0, that will be equal to q naught L square pi square pi by L cos pi x by L, right, equal to 0, and this would give me x equal to 0. No, uh, no, so this would give me cos pi x by L equal to 0, and this would be 0 when pi x by L is equal to pi by 2 x by L is equal to 1 by 2, that is x is equal to L by 2. Okay, so M max is M at x equal to L by 2, that is q naught L square pi square sin pi by L times L by 2. And this would be equal to Q naught L square by pi square. Thus our answer, correct answer would be option B, Q naught L square upon pi square. Okay, so this is looks a simple question. You just need to use a simple trick to find the maximum minimum. And one thing you need to keep in mind is this relation that you need to remember, that m is the bending moment, m is equal to ei times double derivative of the deflection curve. Okay, moving on to the next question. Okay, the sixth question is, a simply supported beam of span L and of uniform EI is subjected to concentrated load P at the center. Maximum deflection of the beam is. So, uh, uh, so I can give you the direct answer as given earlier in the starting of this session, but for this question, let's try to do it in a more traditional way. Okay, so let's first draw the system. What is it given? Uh, we are given with a simply supported beam, and there is a concentrated load at the center, L by 2, L by 2, and EI is the flexural rigidity, and I can take A, B, C. Now, for this system, what would be my bending moment diagram? If you remember, the reaction at A, B would be equal to P by 2, P by 2. So thus we can directly draw the bending moment diagram, and it will come out to be kind of this, and it would be the value here PL by 4, right? So this is at A, this is at C, this is at B. Yeah, now I can write using moment area method, because we want to find the maximum deflection, right? And maximum deflection would be at the center itself. Yeah, so to using moment area method, first thing, slope at A would be equal to what? If I write theta A times L, right, and this would be equal to complete thing 1 by 2. I'm taking it about like PA, and this would be equal to theta A times L, and half times complete span L, and PL by 4, and distance would be L by 2. So so this would give me theta A as PL square 84416 M by EI, right? PL by 4 EI. So this is a moment diagram. So if I write M by EI, M by EI would be the same thing, just the values, it would be PL by 4 EI. So theta A comes out to be 4 for the 16 EI, and this would be clockwise. Now let's find what would be the slope at B. Okay, the slope at B can be found using kind of theta BA, and this is theta B minus theta A, and it would be equal to the area between these two. So this would be like half into PL by 4 EI into L, right? And if I solve this, theta B comes out to be PL square. So this is square by ATI. This is anti-clockwise. So plus theta A is clockwise. So if I use the sign convention as anti-clockwise to be negative, then this would be minus plus theta A, this would be PL square by 16 EI, and thus theta B would come out to be minus PL square by 16 EI. That is theta B would be equal to PL square by 16 EI anti-clockwise. Now we want to find the deflection at C. So our objective is to find the deflection at C. To find that, we need to take theta A like from A to C. Okay, so theta A momentum L by 2, then deflection at the C and TCA. Okay, we know theta A is PL square by 16 EI times L by 2. We need to find delta C. TCA, so this would be equal to what? So bending moment diagram. See, so this is area between A and C is half into L by 2 times PL by 4 EI, and the moment is so from this side L by 2 is 1/3 of L by 2, right here, 1/3 of L by 2, that would be L by 6. Okay, now let's solve this. PL cube by 32 EI minus PL cube by 6 for the 32 96 EI 4 for the 16. So yeah, this would be equal to Q by 3 minus 2 upon 96 EI, that is, it will be equal to PL cube by 48 EI. So this is what we'll have. So this would be the maximum deflection, and that would occur at the center, right? And the value is PL cube by 48. Yeah. The answer is option B. So this is I already told you guys to remember it. If you remember it, this is the case here. Simply supported beam, concentrated load applied at the center. So the deflection value comes out to be PL cube by 48 EI. So you guys can remember this. This is a standard one. Yeah. I hope this is okay for you all. So moving on to the next question now. Question number 7. We are given with a cantilever beam ACB that supports two concentrated loads P as shown in the figure. One concentrated load is applied at L by 2 from the fixed end and the other one is applied at L from the fixed end. We need to find the deflection of the point C. C is this midpoint. Yeah. So let me draw this again properly. Okay. Now this is a load at the end, load at the center. A, C, B, L by 2, L by 2. And EI is the flexural rigidity. Okay, now first thing first, draw the bending moment diagram. Bending moment diagram, and that would be equal to what? So this would be equal to so if I take the case of only the load at the load applied at the free end, that is at B, so that will give me bending moment diagram as this, and this would be equal to PL. But there is an additional load applied at this C, so cause of that my additional bending moment diagram contribution would be PL by 2 from C. Okay, now these are like combined. This combined is my bending moment diagram. Okay, so M by EI can be M by EI diagram can be generated by just dividing this thing by 1 upon EI altogether. Now we want to find the deflection of the point C. For okay, yeah. The deflection of point C can be calculated by like using moment of okay, we want to calculate this, right? So using moment area method, deflection of C with respect to A, it would be equal to moment of area of M by EI diagram between C and A. Between C and A about about C. So we want to calculate deflection at C. This would be the moment of area of M by EI diagram between C and A. So first thing, okay, between C and A, right? So this can be uh, like divided into two parts. So this would be equal to what, PL by 2, and this would be equal to PL by 2, because here the value is PL by 2. Now we can from compute the moment. Okay, so first take the rectangular part. So this is equal to PL by 2 EI times L by 2, and moment would be L by 4, right? Plus now the triangular part of the same thing. So half into base into height. So PL by 2 EI into L by 2 into, so moment about uh, uh, C, that would be equal to PL by 2 L by 2, and no, so this would be we are taking with respect to A, right? Between C and A, about A. So this would be equal to 2/3 of L by 2 plus half into, now the contribution from the load applied at the C. So this would be equal to PL by 2 EI, again L by 2 times 2/3 of L by 2. So this would be equal to, let's calculate it. So first thing will give me PL cube by 4 to the 8 to the 16 EI. Now this one L by 3, so L by 3 again, so in the numerator it would be PL cube by EI. I need to just calculate the denominator part. So 2 to the 4 to the 8, 3 is a 24, plus, so this is also the same, the 24 EI. Now let's calculate this. So this would be, if I add this 2, it will be 12 and 16. So make it 48. So this would be 3 plus 2 plus 2 PL cube by 48 PI, and this is equal to 325 7 PL cube by 48 Ti. Okay, yeah, so answer is option B, 7 PL cube by 48 Ti. Okay, yeah, to find the deflection at the C, we first calculate the bending moment diagram of the given system, and so deflection at C can be computed by taking moment area between A and C, and since we know the deflection at A would be equal to 0, so we can directly, like, this is actually delta C minus delta A, but we know delta A is equal to 0, so we directly know that the value would be delta C. Okay, now moving on to the next question. Yeah, so this is also a good question. The question is the deflection curve of a simply supported beam of span L is given by the following equation, and the system is simply supported beam of span L with x as our longitudinal length and y as our transverse length, transverse direction. So the question is the load on the beam AB is correctly described by. The options are like first option is point load Q naught kilonewton at the center of the beam. Option B is uniformly distributed load of intensity Q naught kilonewton per meter. Option C is uniformly varying triangular load of maximum intensity Q naught kilonewton per meter. And option D is parabolic load of maximum intensity Q naught kilonewton per meter. Okay, so in this question we are given with the deflection curve. We need to find what type of loading is applied in the system for which we are getting the given deflection curve. Okay, so let me write the deflection curve given as Q naught x 360 L upon 12 minus 15 L square x square plus 3x to the power 4. So this is equal to y, can use, right, as per given. Now we know the relation of loading, load Q is equal to what, EI times fourth derivative of y with respect to x, d4y dx4. Okay, this is relation of loading with respect to my deflection curve. So we just need to compute, for this we need to compute the fourth derivative, right? So let's compute it. So what would be my first derivative? It would be equal to Q naught 360 LEI to L4 minus 15 L square 6 square plus 3x4 plus Q naught x by 360 LEI minus 30 L square x plus 12 x cube. So this is my first derivative. Let us calculate the second derivative. Second derivative will be 360 LEI. It's equal to again 30 L square x plus 12 x cube plus Q naught. Okay, so this would be kind of 2, then again plus, I'll just take this Q naught x 360 LEI, and this would be minus 30 L square plus 36 x square. Now third derivative would be, take the first one to Q naught 360 LEI If I take the derivative, it would be 30L square plus 36x square, right? And here let us take the derivative. Q naught 360 LEI minus 30L square plus 36x square plus this would remain as it is, 360 LEI and 72x. So I can combine this two and write it as d cube I by dx cube is equal to 3q naught on 360 LEI minus 30L square plus 36x square plus q naught 72 q naught x square by 360 LEI. Now finally the fourth derivative, d4y by dx to the power 4. So this would be equal to 3q naught. That's the correct thing, right? So 3q naught 360 LEI times 72x plus, and this would be equal to 72 times 2, that would be 144 q naught x 360 LEI and so this is equal to d4y dx4, it's equal to 72 times 3 plus 2, 5 by 360 LEI q naught x. This can be simplified again as 36 10 to 10 5 to 2. So this is coming out to be q naught x LEI. So EI d4y dx4, it comes out to be q naught x upon L. Okay, this is 3. So from 2 and 3, from 2 and 3, we can see our load Q comes out to be Q naught x by L. Okay, so this is for sure cannot be the case for the constant load applied, point load applied at the center, nor the so our Q, like I'll just write it here, Q comes out to be Q naught x by L. So this, the first option, it cannot be there because it's a varying load, right? It depends on x. So first case it can't be there. Uniformly distributed load of intensity Q naught. So for this it should have been just Q equal to Q naught or Q naught by L. It should not depend on x. So this is also not the case. Uniformly varying triangular load of maximum intensity Q naught. So this would be the case because at x equal to 0 it would be the minimum, and at the and the maximum intensity that x equal to L, it would be having the maximum intensity. The correct answer would be option C. So the question was, we were given with the deflection curve of a simply supported beam of the span L. We need to find the loading condition, like for what loading condition we are getting this deflection curve. So first thing, we wrote the deflection curve itself, and we know the relation for the loading with the deflection curve is this. Equation number 2, that is q equal to ei times fourth derivative of the deflection curve with respect to the x. Then we just try to find that, and we got is that q is equal to q naught x by L, and consequently the correct answer would be option C, uniformly varying triangular load of maximum intensity q naught kilonewton per meter. That is our loading condition is this is q naught. Okay, and this is the span length L, A, B, and x is here, y is here. That is x equal to 0 here, x equal to L here. Okay, this is it for this question. Moving on to the next question now. Question number 9. A simply supported beam of flexural rigidity EI and length 2L carries a concentrated load P at its midspan, and the deflection under the load is delta. If a cantilever beam of same flexural rigidity and length is subjected to a concentrated load P at its free end, then the deflection at the free end will be. So this question I'll try to just solve using the formula which I provided you. So the first part of the question is, we are given with a simply supported beam. It has a span length of 2L and flexural rigidity as EI, right, IB, and carries a concentrated load P at its center, C. So deflection under that load is delta. That is delta C is equal to delta, and we know as if I will show you, I gave you the relation. It's like if the span length is L, so the deflection at the midpoint comes out to be PLQ by 48 EI. So for this, for the current question, it will be equal to PL, span length is 2L cube by 48 EI, and this will be equal to this will give me delta is equal to 2 to the 4 to the 8. This is PL cube by 6 EI. Yeah. Okay. Now the second part is, we are given with the cantilever beam of same flexural rigidity, implies that EI is the same, and length L is subjected to concentrated load P at its free end, and the deflection, I'll just write it as A dash and B dash. So we need to find what would be the deflection at the free end. The deflection at the free end is equal to PL cube by 3 EI. If I will show you this, guys showed you earlier, for a deflection case of a cantilever beam when the concentrated load is applied at the free end with the span length L and EI as a flexural rigidity, deflection comes out to be PL cube by 3EI. So we will use this relation now. In this case, so PL cube by 3EI. Now this can be delta B dash PL cube by 3EI can be written as 2 PL cube by 6EI, right? And this is equal to 2 delta, right? This correct answer would be option A, 2 delta. Okay, please look into it. Whether if you have any doubt, you can just ask me anytime. Okay, hope this is okay. Moving on to the next question. Question number 10. A cantilever beam, so this time system is a cantilever beam, is subjected to a concentrated load P and a moment M at the free end as shown in the figure. The angle of rotation at the free end B is. So should I give you time to calculate this or should I solve this? Can you guess which would be the correct answer out of the 4 options provided? We'll just magnify it a bit. So this is the case. A cantilever beam is subjected to a concentrated load P and a momentum at the free end. So the load P is acting downwards while the momentum is acting clockwise in the free end, at the free end. So we want to calculate the angle of rotation at the free end, and the options are provided. Given with the A, B, span length L, and EI as the flexural rigidity. Okay, I'll try to solve this. Let me know if you feel any doubt. So first thing, bending moment diagram. So contribution from the concentrated load for the case of bending moment diagram would be PL, and this is acting downwards, so kind of it will contribute into the negative bending moment, plus contribution from the concentrated moment. I would take this, and it would be M all over, and it would be positive. So this is the cumulative contribution of bending moment diagram. Okay, we want to calculate the slope at B. The slope at B can be computed by just computing the area between A and B, because we already know what would be my slope at A, that is equal to 0. Okay, so using moment area method, slope at P is theta B, right? And theta B is equal to theta B minus theta A, that is theta BA, and this is equal to area of M by EI diagram between A and B. Thus theta B would be equal to, so first from the negative 1, that is from the concentrated load, so it would be minus 1 by 2 of PL by EI, sorry, yeah, PL by EI times L, right? And from the concentrated moment, that is positive, and that would be M by EI times L. Thus theta B would be equal to minus PL square by 2 EI plus ML by EI. Thus our answer would be option C, minus PL square by 2 EI plus ML. No, not option C, option B, PL square by 2 EI plus ML by EI. Okay, yeah. So this is like trying to find using the moment area. You can also I'm just repeating again and again, you can just remember this 5 standard thing which I provided. You can use this also to directly compute it. So for this case, to solve the current problem, you need to use this one and this one, right? Yeah. Okay, moving on to the next question now. I hope this is okay. Yeah. So question is, the deflection at the free end of a cantilever beam of span L due to a moment at the free end is. So earlier the question was the slope thing, right? This time the question is asking about the deflection at the free end of a cantilever beam span due to a moment at the free end. Okay, the question is cantilever beam with the moment M at the free end, span is L, and this is A, B, what is delta B? This is the question. So with the thing which I provided earlier, you can directly say what would be my correct answer. It is kind of this, right? ML square by 2AI. But this time let's try to solve it using moment area method. I'm just trying to mix it so that it might help you to like solve it. So for this case, what would be a bending moment? This would be M, right? Now M by EI. Now to find the deflection using moment area method, deflection at the free end B, it's equal to moment of area between A and B about B. Thus, delta B would be equal to moment of area between A and B about B. So, first thing, what is the area between A and B? That is M by EI times L, and the moment arm would be L by 2. Thus, deflection comes out to be ml square by 2EI. This is it. The answer is option C, ml square by 2EI. Yeah, okay, I'm seeing it now is we could have just found the answer using the dimension wise also. We could have like tried to solve using the by eliminating all the incorrect dimension for the deflection. Okay. Moving on to the next question. So this is a very good question. Uh, the question is, what is the reaction at the hinge joint B for the beam as shown in the figure? So if you see the figure, there is a fixed beam AC. In the midpoint, there is a hinge point B, and between A and B, a UDL is applied with the loading W kilonewton per meter. So we need to find what would be the reaction developed at the hinge point B. Okay, I'll just draw this again. Okay. So if you understand the scenario, what will happen is this is a hinge, right? So due to this loading, this point will try to go down, and since it is connected to this section, uh, this part will try to resist it, right? So consequently, what will happen if we take the case part by part? Due to this loading condition, uh, it will try to go down, but there would be a reaction force developing here. Okay, while uh, to have an equilibrium of force, uh, same reaction would be developing here. Now, this reaction force will uh, make certain that this due to this loading condition, it will displace to a certain extent, and due to the same reaction force in the center, this will go down. So what will happen is to maintain the continuity of the beam, the deflection for this AB and this is BC, So if I say deflection at B for this beam BA should be equal to deflection of at B for the section BC, right? To have the continuity in the system. I mean to say this point B would displace by a certain amount delta B, and this should be equal for the both case if I take AB or BC, right? Now let us solve this, like whatever scenario I'm just saying about it. LEI, this is LEI. Okay, now let us solve it. Now taking section AB, deflection at B, that is BA, would be equal to what? Now I'll just try to use the formula which I provided you earlier. So if you see, there are two loading condition. One is UDL and other one is concentrated load. Okay, so for UDL case, if this is the one, WL4 by 8EI. Okay, just let me write it down, this thing first. So due to low this UDL, uniformly distributed load, it would be equal to WL4 by 8EI, and due to the reaction force, and since it is acting upwards, due to the UDL it will the deflection would be downwards, while due to the reaction force it will try to decrease this deflection quantity, and it would be equal to RL cube by 3EI, as we have found it earlier also. Okay, now considering section BC. Section BC is a cantilever beam, and cantilever beam, and it is been acted upon by concentrated load R, that is acting downwards. Thus the deflection would be equal to RL cube by 3EI downwards. Now using condition 1, I'll just write, using 1 we can write WL4 by 8EI minus RL cube by 3EI equal to RL cube by 3EI, and this is equal to I hope I am writing it correct. Yeah, so this would be equal to WL4 by 8EI, and this would be 2RL cube by 3EI. EI cancel out. L cube would be this. This would be equal to 3WL by 16 equal to R. Or I'll just write it. The reaction force R will come out to be 3WL by 16. Yeah. Okay, so kilonewton. Answer is option D, 3WL by 16. Okay. So now moving on to the next question. Question number 13 is the ratio of maximum deflections of a beam of length L simply supported at its ends with an isolated central load that is W kilonewton, and that of with a uniformly distributed load W kilonewton over its entire length. Okay, this is again similar thing, but now the case is the two cases are both are the simply supported cases. First case is a simply supported beam with a span L, and there's a concentrated load or isolated center load W acting at the center. Okay, this is the first case. The second case is there's a simply supported beam with the same span length L. For both cases, flexural rigidity is EI, and for the second case, there's a UDL acting all over, and its value is W kilonewton per meter. So W kilonewton, where W is equal to W by L. Okay. So we need to find the ratio of maximum deflection of these two cases. Now, again, so let's just find it. A, B, C, A, B, C. So again, I'll just show this one. Simply supported beam, two cases. When the central load, isolated central load is acting at the center, maximum displacement is at the center, and its value is PLQ by 48 EI. And when the UDL is acting, uniformly distributed load, the maximum displacement is again at the center, and its value is 5WL4 by 384 EI. So we'll just use this. Now, so delta C would be equal to, for this case, is WLQ by 48 EI, and for this case I'll just write delta C for this. This would be equal to 5 by WL4 by 384 EI. Now we can write W as this relation, right? Delta C is 5. If I use that relation, then it will reduce to WLQ by 384 EI. Now take the ratio of these two cases, delta C upon delta C. We'll get 1 upon 48 upon 5 by 384. This can be computed now as 384 by 5 times 48, and this comes out to be 48 8 times, so this would be 8 by 5. Let me see, yeah, 8 by 5. Okay, so if I see of all the options, 8 by 5 is not there. Okay, so this is 3 by 2, I cannot make it 5. Yeah, so this one, if I see option C, 3 8 4, this is actually 8 by 5. So correct answer is option C. Okay, so this is also a very straightforward question. We just need to find the deflection at the center for these two standard cases. There's a relation provided for the UDL that small w is capital W upon times upon the entire span length, and we just substitute it, then take the ratio of it. We are getting is 8 by 5, and that is equivalent to option C, that is 24 by 15. Okay, I hope no issues pertaining to this question. Okay, moving on to the next question. Question number 14. If the depth of a simply supported beam carrying an isolated load at its center is doubled, the deflection of the beam at the center will be changed by a factor of. So this is similar to the question number 2. In this question, the depth was tripled, and the current question, it says it's doubled. So if you just look into that, so what we discussed earlier is a deflection is inversely proportional to I, and I is directly proportional to dq, depth, right? Thus deflection is inversely proportional to dq. Since our depth is doubled, or if I write d2 is twice of d1, so delta 2 would be, we need to find what is delta 2 by delta 1, right? We need to find this. So using this relation, my delta 2 by delta 1 would be equal to d1 by d2 cube, and this would be d1 twice of d1. This would be equal to delta 2 by delta 1 is 1 by 8, and this is what we need. Thus our answer would be option D, 1/8. So as we increase the depth of the beam, our deflection at the beam at the center will change by a factor of 1 by 8. Now moving on to question number 15. This is a bit a calculation is required in this case, but this is also an easy question. So let's do this. Question is a 15-meter long simply supported steel beam of breadth 120 mm and height 750 mm is uniformly loaded over the entire length with W equal to 120 kN per meter. The value of maximum deflection of the beam is, assuming Young's modulus or modulus of steel, modulus of elasticity of the steel is equal to 200 GPa. The options are 93.75 mm, 83.75 mm, option C 73.75 mm, and option D is 63.75 mm. So this is similar what we have discussed. This time we are just like putting the values and directly calculating what we need. So first thing first, let's draw what is my system. What is the structure provided in this question? It's a simply supported beam. Okay, let me first thing write it like this. In the span length, then it's a UDL W. Okay, and it is having a rectangular cross section P or D. Okay, I'll just substitute what are the values provided. So length is given as 15 meter. 15 meter. So okay, I'll just convert this into millimeter as 15,000 mm. Now other thing is breadth, that is 120 mm. Height or depth, it's 750 mm. Uniformly over there with UTL value as 120 kilonewton per meter. This can be again written as 120 Newton per mm. E still is given as 200 GPa, that is equal to 2 into 10 to the power 5 megapascal, that is 2 into 10 to the power 5 Newton per mm square. Now let's calculate, we need to find delta max. So this is A, B, C at the center. For this case, delta max would be equal to deflection at C. And if you see, this is the case of simply supported beam with the UTL. I'll again show this. So for this, it is equal to 5WL4 by 384 EI. I'll just use this relation. That is 5WL4 by 384 EI. And just substitute it now, the values. The 5W is 120, L is 15,000 to the power 4, 384, E is 2 into 10 to the power 5. Okay, I is, I'll write it here, it's PD cube by 12. Okay, so then just substitute it here. 120, D is 750 cube upon 12. Now all thing is left is to calculate. So we'll just calculate now. So 5 into 120 into 15,000 to the power 4 into 12 divided by 384 divided by 2 divide by 120 and divide by 750 cube. And it comes out to be, if you calculate it yourself as well, it comes out to be 93.75 mm. Thus correct answer is option A, 93.75. So this is what we have been doing exactly, just this time we need to substitute it. And if you know what I have been doing in earlier sessions also, that I used to convert all the length units in mm and keep the force unit as in Newton, so that my stress thing, everything would be in Newton per mm square, because that is easy in calculating. So since deflection is having a length unit, and the correct answer would come out to be in mm. Okay. Now moving on to the last question of today's session. Okay. Yeah. So for this, okay. So I can directly use the moment area method and solve this for the given question. Okay, let me first uh, tell what is the question. Question number 16. A horizontal cantilever B of uniform section and length L carries two vertical loads W1 and W2 as shown in the figure. Find the deflection at the free end. So one load is acting at the free end while the other load is acting at a distance a from the fixed end. We need to find what would be the deflection at the free end due to these two vertical loads. So we can directly calculate using moment area method and find the deflection. Uh, okay, let me draw this. I'll write it A as this fixed end, B as the free end, and C as the load acting at a distance A from the fixed end. Mm, now, mm, okay, let us draw the bending moment diagram. Now, due to W1, my bending moment diagram would be this W1 times L, and this I'll take it as positive, while yeah, so this would be kind of W2A minus. This is cumulative contribution. I need to find what is deflection at the B due to this cumulative contribution. So using moment area, deflection at B is equal to moment of area between B and A about a moment of area of M by EI diagram between B and A about B. So for this, let us see from the contribution from the positive one W1L. W1L, what would be the area? Half into W1L upon EI times L, and the moment it would be acting about 2 by 3 of L, 2 by 3 of L, right? Minus minus contribution from the W2. So contribution from W2, from B to C there is no bending moment, right? So from C to A only contribution is there. So for that, half into W2 AEI times, so the span is L minus A for this, and the distance would be no, this is, the span is L, and the moment arm would be uh, L minus A is this part, so L minus A plus 2/3 of A. So this is it, what we want to find. Let me write it again, then simplify this thing. So this will come out to be W1 L cube by 3EI minus W2 A square by 2EI L minus A plus, so if I see the option, one includes L minus A, so I'll just divide this into two parts like this. Reflection at P is W1 L cube by 3EI minus W2 A square by 2EI times L minus A minus W2 A cube by 3EI. This is it. Let's tally which of the option is correct. So W1 L cube by 3AI, so this won't be the case. W is also not the case. W1 L cube by 3AI, not the plus, minus 1, so this will be the case. W2 A cube by 3AI minus W2 A square L minus A. Yeah, option D. So this is it. This is this wraps up the today's discussion session. If you have any doubt pertaining to any question to what we have discussed in today's session, you can ask. If you don't find any questions now, you can like post it in the discussion forum also, if you may. Okay. So let me know. So we'll end the session now. If you have any more doubts, you can like post it in the discussion forum. Okay. So see you in the next weekend. Uh, on Saturday 4 to 6 p.m. for the 10th discussion session. Yeah. Okay. So bye.
Okay,
Take
sir.
care. Have a nice day.
Thank you.
You're welcome. Bye.